Hello and welcome to MakeLearn 360. In this video, I want to explain to you response to excitation. All right. So whenever we say excitation, we want to talk about the fact that our system is actually um, giving some external force. And usually this external force will be of the form a repeating force. All right. So mostly our external force F here will mostly be some form of repeating force. All right. And usually this repeating force will be of the force harmonic force. It will be of the form which is the harmonic force. So whenever I say a harmonic force, a harmonic force simply means a force of the form F naught sine omega t or F naught cosine omega t. There are several forcing functions, but mostly, you have the harmonic force. All right. So basically, what we have here is actually a force damp. So basically, we want to look at the response to a forced damp vibration. In this video, I want to do force damp vibration with you. All right. So let's draw the free body diagram. First of all, let's draw the free body diagram. I have my mass here. Okay. And then I have a displacement right here, positive in this direction. Now, this is the external force, which is a form of a repeating force. And then, there is a spring here, right? So as I give it the displacement, as I give my mass a displacement, the spring will try to push it back, kx, isn't it? Now, we are assuming that this surface is smooth and then frictionless, and therefore, we will not add friction, all right? So basically, that is it. This is the free body diagram. This is the free body diagram. So from here, we are going to apply Newton's second law, which says that summation of forces positive in the direction of motion to be mass times acceleration. Now, applying this, applying Newton's second law, I have minus kx because the kx is against the direction of positive displacement plus f of t should be equal to mx dot dot. Rearranging this, I'm going to get mx dot dot plus kx should be equal to f of t, where f of t is any harmonic force at all. So in this course, we're going to look at harmonic forces. So let's assume that our f of t is a harmonic force given by um, some f naught sine omega t. So if I write f of t as f naught sine omega t, then I'm talking about the fact that this f naught is actually the magnitude of the harmonic force, and then the omega is the frequency of excitation or the frequency of the harmonic force. All right. Now, over here, I have gotten the equation of motion, and this equation of motion is actually a differential equation. The differential equation. If I want to solve this, I need to go back to my differential equation class. All right. Now, what happens is that this differential equation is actually a second order system. So this is a second order equation. Second order because the higher order or the highest derivative is 2. That is double x, x double dot, right? But this is actually non-homogeneous. Why is it non-homogeneous? Non-homogeneous because the right hand side is not equal to 0, right? And then you can also talk about the fact that it's actually a linear system, and then constant coefficient system. And then you can also say that this function is actually this function is using differential equation. You can say that this is an ordinary differential equation. So ODE, ordinary differential equation. All right, enough of the differential stuffs. Let's get back to our vibration. Okay, So you want to ask yourself, is there a solution which if I differentiate and I put this into it, it will fit? By the way, let's try to look at it this way. This equation is non-homogeneous, right? It means this equation has two parts. It has the homogeneous, or what we call the complementary, um, and then the particular solution. So the homogeneous, okay, let me put it this way. The homogeneous solution, then the particular solution. All right. In terms of response, I can also call this as the homogeneous response or the natural response or the transient response. Okay, so this is, we call it either the natural response or the transient response or the homogeneous solution. Okay. All right. But this part of the solution, we call it the forced response. So either you call it the forced response or you can call it the particular solution, or you can also call it the steady state. Okay, so you can also call it the steady state response. All right, you can call it the steady state response. Okay, now what happens is that the homogeneous response. So if I say the homogeneous response, it is that part of the response for which mx dot dot plus kx is equal to 0. And that is the homogeneous response. In fact, we have done this already in a previous video where we said that for this one, this is a free undamped. The homogeneous response is going to be A cosine omega nt plus B sine omega nt, which is also the same as what? A sine omega nt plus phi. All right. Now, what happens is that this response, which we are calling the transient response, is a function of the initial conditions. So we have what we call initial conditions or initial values. Okay, initial values or initial conditions, right? However, the part of the solution SP of t does not depend on the initial conditions, and that part of the solution depends only on the forcing function. All right, so this is the forcing function, this one. So we are saying that our particular response, which is SP of t, depends only on the forcing function. And what is the forcing function? The forcing function is this one. Therefore, what happens is that if my forcing function is f of t, f naught sine omega t, then usually the response, which is SP of t, which is the steady state response, will also follow some x naught sine omega t. All right. So basically, what we are trying to say is that the homogeneous response or the natural or the transient response depends on the part of the equation for which this side is 0. And then that is actually depending on the initial values. All right. However, the SP of t, so we are saying that the SP of t depends on f of t, which is what? F naught sine omega t. So let me write the equation again. So I have mx dot dot plus kx to be equal to f naught sine omega t. All right. Now, at this point, you want to ask yourself, is there a function x of t, which when I differentiate, if I differentiate twice and I add it to the function itself, to be equal to this? The answer is yes. And that is actually your particular solution. Okay. That is your particular solution, which you said is what? X naught sine omega t. All right. So now, at the end of the day, what we are actually interested in is that we are after the x naught. We want to know the value of the x naught. And that will be our solution, the amplitude. Okay, that will be the dynamic amplitude. All right. So let's finish getting the value, and then I'll give you the terminologies. So let's find the first derivative. The first derivative of this is going to be what? Omega x naught cosine omega t. Is that right? So treat this as a function of a function. And then you realize that if you differentiate sine omega t, you get cosine omega t, and you multiply through by what is inside, which is the omega. The second derivative of this is going to be what? Minus, again, we are going to differentiate cosine to get, so if you differentiate sine, you get cosine. If you differentiate cosine, you get minus sine. And we are saying that it's going to be minus omega squared x naught sine omega t. So always, if you differentiate a function of a function, you differentiate the whole thing, then you multiply by the derivative of whatever is inside. And then we are differentiating omega t with respect to time. That's why we are getting omega. All right. Now, at this point, I want you to go back. So you are saying that the mass multiplied by this acceleration or the second derivative, you are saying that this plus the function itself, that is x naught sine omega t, you are saying that this is equal to f naught sine omega t. Is that right? Now, if this is the case, then I can clearly say that over here, I can write this as x, some x naught sine omega t will come out, right? Then I can write what? K minus m omega squared. That is if I rearrange it to be equal to f naught sine omega t. Now, since sine omega t is here and then sine omega t is also here, then we can say that this is equivalent to just writing omega squared to be what? F naught. So what is x naught then? X naught is going to be f naught divided by k minus, all right, so x naught is going to f naught divided by k minus m omega squared. And this s naught is what we are calling the dynamic amplitude. Dynamic amplitude. Dynamic amplitude. Is that right? So what this means is that if I want my total response now, my total response is my homogeneous response, then my particular response, which is what? A cosine omega nt plus B sine omega nt, and then plus what? X naught. Now I know X naught. So F over K minus M omega squared sine omega t, where the F naught over K minus M omega squared is the dynamic amplitude. So this is what I'm saying. We said earlier on that our homogeneous response is A cos omega nt, and our particular response will come from the Poisson function. And we agreed on that it is actually x naught. So we said that this is our particular response. And so, in fact, this is the response, but the x naught that we want over here, this x naught, that is what we have over here. That is the x naught, all right? Now let's try to play around the x naught small. Let's try and play around the x naught. Okay, so with this, let me say I want to divide through by the mass. So dividing through by the mass, dividing through by m, which is the mass, my x naught is going to be f naught divided by small m all over k divided by m minus m omega squared divided by m. So I'll get small f naught, which is also called the force per unit mass. Okay, k over m. In fact, the natural frequency omega n squared is k over m. So I can say that this is omega n squared minus the m will take the m away, so we'll be left with omega squared. All right. Okay. So let's talk about something here. This function will become discontinuous, or it is actually a discontinuous function, isn't it? And it becomes discontinuous whenever omega squared minus omega is 0. This function becomes discontinuous. In other words, at this value, what happens is that this function, the value of the x naught, so the value of x naught for which this omega n squared minus omega equals 0 becomes infinite, right? Infinity. Because why? Because if the denominator, if I have this to be divided by 0, then it's going to be infinite, right? So making this the subject, I can say that omega n equals omega. And this is what we are calling resonance, okay? Resonance. So whenever I have a vibrating system, then I have a resonance, then I'm calling the term where the system becomes discontinuous, or I have higher amplitude. Don't forget that we said that the x naught is the dynamic amplitude. Okay, this is the x naught. And then we are saying that the value where the omega n squared minus omega squared becomes equal to 0, or becomes omega. So in other words, all right. So this omega n is what we call the natural frequency of the system, which is a constant for every given system, the natural frequency. And then the omega is what we call the operating frequency, sometimes called the driving frequency, or sometimes called the excitation frequency. So either of them is correct. Either you say operating frequency, driving frequency, frequency of excitation. Now we are saying that this um, omega n, when it is exactly equal to omega, then the phenomenon which we experience is what we are calling resonance. And what does it mean? It means that at resonance, the amplitude becomes infinite. It means that you are going to divide by 0. That is going to be infinite. So you are going to get large amplitude at uh, at resonance, and so it must always be avoided. So must be avoided. And this is the reason why whenever soldiers are marching and they get to a bridge, they are told to walk. Other than that, if they decide to march, they will collapse the bridge. All right, they will collapse the bridge. Okay, so basically at this moment, we've been able to calculate x naught, right? Let's try and play around x naught again. So we said x naught is what? F naught over k minus m omega squared. Let's divide through by k and let's see. So dividing through by k. So dividing through by k, what will I get? I'm going to get x naught to be equal to f naught divided by k, k minus m omega squared all over k over k. All right. Now, let's call some important parameters here. So we are calling a certain parameter static deflection. So this is static deflection. And the static deflection, we are calling it F naught divided by K. All right. That is what we call the static deflection. And then we are also calling, all right. So it means this is going to be static deflection divided by K over K is 1, right? But what is, let's do some gymnastics here. M omega squared over K. You know, what is M over K? Can you give a thought about it? Omega n squared is actually K over M, isn't it? So if omega n squared is K over M, then it means that M over K is actually 1 over omega n squared. So it means if I have M over K omega n squared, it's like multiplying 1 over omega n squared by what? Omega squared. In other words, if I have, so this is what I'm saying, if I have M omega squared over K, then this is equivalent, is the same as omega squared over what? Omega n squared, which is the same as doing what? Omega over omega n all squared. Now we have gotten another important parameter in vibration again, which is tau, which we call the frequency ratio. The frequency ratio. Why are we calling the frequency ratio? The frequency ratio because it relates our natural frequency to our operating frequency. All right. And so I can simply say that The x naught is the static deflection, which is f naught over k divided by 1 minus the tau, which is the frequency ratio or square. And in fact, this is actually one of the simplest way to write this equation. Now let's do something here. There is a certain parameter called x naught over static deflection, which is going to be 1 over 1 minus tau squared. And we call this the amplification factor. So amplification factor, or it's also called, so you can also call this the amplitude ratio. Okay, so the amplitude ratio. Why are we calling it the amplitude ratio? It is comparing the static amplitude, which is the static deflection, and it's comparing it to the dynamic amplitude, right? Okay, so that is the amplitude ratio there for you. All right. All right, so at this point in time, I want to end the video here, but we've been able to show that if I have a system which is mx dot dot plus kx to be equal to f naught sine omega t, in fact, this can even be cosine or sine, then we are saying that the total response will come from what? A cosine omega nt plus what? B sine omega nt plus the x naught. And so I can also express x naught as the static deflection divided by 1 minus tau squared sine omega t. We said that we know our tau, which is what? The frequency ratio. Okay. We said the tau is our frequency ratio, which is what? The operating frequency divided by the natural frequency, right? And we said that the delta is our static deflection, which is given by f naught over what? K. All right. So that is it for you. Thank you very much for watching.